Hello everybody, get ready to do lesson 2.7, part 2 of Algebra 2 Math. Part 3 is available here at this email as well as all the other course materials. 2.7, applying the fundamental theorem of algebra. We got a 32-point classwork sheet today, 0 points of note taking. And starting off, we have a classwork sheet, page 1 on your classwork sheet. And if you don't have a classwork sheet, people, you're not going to know what's going on here too well. Unless you're taking great notes and you're doing a lot of pausing and replaying. That's fine too. But it's a lot easier if you get your classwork sheets. Also, in example 2, notice that 0 is 2. And this you would get from your previous classwork sheet. If you don't know what's going on here, it's because you don't have part 1. So I'm just saying, the 0 is 2 plus I times square root of 3 and 2 minus I times square root of 3 are complex conjugates. This illustrates the first theorem given below. A similar result applies to irrational zeros of polynomial functions as shown in the second theorem below. This is classwork sheet page 1. So a key concept here, complex conjugates theorem. If a f is a polynomial function with real coefficients and a plus bi is an imaginary 0 of f, then a minus bi is also a 0 of f. The irrational conjugates theorem. F is a polynomial function with rational coefficients and a and b are rational numbers such that square root of b is irrational. If a plus radical b is a 0 of f, then a minus radical b is also a 0 of f. So that's something that comes in real handy if you're trying to find zeros. Using zeros to write a polynomial function, write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1 and 3, and 2 plus radical 5 is 0. So we have leading coefficient of 1 and 3 and 2 plus radical 5 is 0. So because coefficients are rational and 2 plus radical 5 is a 0, 2 minus radical 5 must also be a 0 by the irrational conjugates theorem. Use the 3 zeros and the factor theorem to write f of x as a product of the 3 factors. So how will we go ahead and do that? Here are our factors. Here's our zeros. So we know this is the factored form of a polynomial. And so we're going to regroup like terms together, x minus 2 minus radical 5, and then x minus 2 plus radical 5, all times x minus 3 here. So when we multiply these together, we get x minus 2 squared minus 5 times x minus 3. And then when we multiply those together, we get this situation here. We expand this out here to this minus 5. And then we further simplify, combining like terms, etc. And we have this situation here. And then when we multiply this together here, we get this. And then when we combine like terms, we get this situation here. So there's our polynomial by evaluating f of x at each of its 3 zeros. Okay, so we do that. So we're going to plug in 3 here, see if it comes out to be a 0. It does, so it checks there. We plug in 2 plus radical 5, and what do we get from that? We get a 0 from that as well, even though it's pretty elongated here. That's quite an elaborate situation there. And then since f of 2 plus radical 5 equals 0 by irrational conjugates theorem, f of 2 minus radical 5 would also equal 0 by that theorem. Okay, let's do this. I've got to practice here. Write a polynomial function f of least degree that has radical coefficients, a leading coefficient of 1, and the given zeros. Same situation down here for you students. So you have, well, I'm going to let you do it. Okay, let's do what I got to practice here. Here are our zeros. So we know that this is the factored form of the polynomial. We multiply those together, we get this here. from their first two binomials times that, and then we further multiply, we get this situation. So that was our polynomial. Here's our polynomial by going from zeros to that. Descartes' rule of signs. René Descartes found the following relationship between the coefficients of a polynomial function and the number of positive and negative zeros of a function. So here's our standard form of a polynomial here, decreasing degrees of terms with real coefficients here. The number of positive real zeros of f is equal to the number of changes in the sign of the coefficients of f of x, or is less than this by an even number. So what does that mean? The number of negative real coefficients of f is equal to the number of changes in the sign of coefficients of f of negative f, or is less than this by an even number. What in the world does all that mean? Use Descartes' rule of sign on this situation, this big gnarly thing here. Determine the possible number of positive real zeros, negative real zeros, and imaginary zeros. So this situation here, we have the coefficients in f of x have three sign changes, 1, 2, and then 3. We have three sign changes. So f has 3 or 1 positive real zeros here. So the coefficients here have 3 sign changes. And then in this situation here, the f of negative x, so when we get through and we power these out, the negative x's in this situation, there's no sign changes here, but we got 1, 2, and we have 3 sign changes here of the coefficients. So the coefficients in f of negative x have 3 sign changes. So f has 3 or 1 negative real zeros. 3 or 1 positives, 3 or 1 negatives. So the possible numbers of zeros of f are summarized in the table below. Positive reals, positive reals, negative reals. Imaginaries, we don't have any. So we have a total of 6 here, or we have 3 and 1, and then 2. So either way, we have 6 zeros in each one of these makeups here of the possibility of real zeros using Descartes' theory of sign changes. Determine possible numbers of positive reals, negative reals, and imaginary zeros for this function here. Students, this is yours here. Pay attention so you can do your Okay, there's our situation there. So how many sign changes do we have? The coefficients in f of x have 1 sign change, so f has 1 positive real zero. And it's just that simple. We have 1 sign change, so we have 1 real. And then doing the negative x here, the coefficients of f of negative x has 0 sign changes, so f has 0 negative real, has no negative real zeros. Possible numbers of zeros for f are 1 positive real and then 2 imaginary zeros. So we have 2 positive, we have 1 positive and 2 imaginary zeros for that polynomial. And that is 2.7, part 2. Part 3 is available here. Worksheets, class worksheets, quizzes, tests, tutoring, etc. Email me. Thank you.